Good evening. How's everybody?
Good evening, Professor. Doing good.
Good. All right, let's get started. I think I'm pretty comfortable we're going to do this lecture in the time that we have. I don't think that's going to be a problem. So we have a little bit of time. When we have a little bit of time at the end of the lecture, I might open the conversation about midterm that we have in about a week and a half. And I'm sure you guys might be starting to wonder what's going on with that. And if there's any homework issues, we could talk about that too. But I'm going to reserve those for the time we have after this lecture. But I would like to start with if anybody has any pressing questions that they would like to ask of me now, please feel free. All right. So tonight marks a departure from flexural design. What we basically have been doing since day one now is the flexural response of reinforced concrete beams, finding the moment, finding phi min, checking the minimum steel, making sure the epsilon sub t is at least equal to 0.005 or otherwise checking maximum steel. All of that has come to a conclusion with our lecture on compression steel. So what we're going to start tonight is a totally different direction. We're going to start shear design. So without further ado, let's see, how do I make this guy disappear? Get out of here. Okay. Let's start talking about shear design. And the first thing I want to say about this whole topic is shear is a measure of diagonal tension. Concrete beams don't actually fail in shear. They fail as a result of diagonal tension. So if I have a reinforced concrete beam supported end to end, dotted line represents the flexural steel. In areas of high bending stress, cracks in the tension zone are vertical. Okay, so if I analyze this beam, I can do a shear diagram. I can do a moment diagram. The moment, of course, is maximized at the midspan of the beam. So where the moment is at its maximum is where you're going to get flexural stresses that are at their maximum. So the compression stress at the top of the beam is maximum at the maximum moment, and the tensile stresses at the bottom of the beam are maximum at the maximum moment. So basically, a crack goes vertical 90 degrees at the point of maximum moment and zero shear. In areas of high shear, cracks are inclined and approach 45 degrees in areas of pure shear. So this region here has high shear, low moment. So the cracks at the end of the beam are basically oriented in a 45-degree angle because there's very little flexural stress or tensile stress. It's almost all shearing stress. And as you go from the end to the midspan, then you get various combinations of shear and flexure. The actual mode of failure, as I noted, is diagonal tension. So beams don't actually shear in the sense of like other materials that can actually shear. Beams develop these cracks at a 45-degree angle. That is the result of diagonal tension. If I look at, there's a little square right there, and if I pull that square right from this crack in this region of high shear, so I look at an element in a region of pure shear, then if I pull that element out, what I'm looking at is that element has shear. So this is vertical shear and the opposite, and this is horizontal shear and the opposite. And there's no, you remember from your mechanics of materials, remember from the section that you did on stress and strain transformation, right? You remember all that? With stress transformation, you have a shear stress, you have a sigma X, and you have a sigma Y. And then you could rotate this element at any angle and calculate the transformed shear stress and sigma X prime and sigma Y prime stresses, okay? So that's what we're looking at here. But at the neutral axis towards the end of the beam, there's no sigma forces on this element. You don't have any significant axial stress on this, you just have shear stress. But the beam is really strong in shear, so the shearing stress is not really a problem. But if you rotate this element, what you'll find is at a certain angle, about 45 degrees, then you have this tensile sigma. You have a 90 degrees rotated, you have a compressive sigma, but we don't really care about that either because the concrete's strong in compression. But it's this rotated at a 45-degree sigma in tension. That's the one that controls because concrete is weakest in tension. And that's why the crack is oriented at a 45 degrees. It's basically lined up with the direction of this plane for the maximum tensile stress. So though the element has only shear stress in the XY coordinate system, when transformed via Mohr's circle, diagonal tension is revealed. And that is what fails it because concrete is much weaker in tension than in shear. Thus, the shear failures are really diagonal tension failures. Okay, any questions on this concept? Okay, so shear is really a measure of diagonal tension. There are many formulations and theories that try to capture the very complicated behavior of beams in shear. Many different models. If you read the structural journal, every couple of years somebody comes out with a new model that seems to do a better job of predicting shear in certain circumstances. But the end of the story is that how much shear it takes to actually fail a beam is it's a wide scatter. There, if you do beam testing, you'll find values all over the board. So what ACI does, ACI 318 takes a fairly simplistic and conservative method to determine allowable shear. Concrete beams may or may not have vertical shear steel to reinforce the allowable shear strength. We will cover shortly when beams are allowed or not to have shear reinforcement. ACI 318-9531 refers the user to section 22.5 for shear strength. ACI 318 section 22.5.1.1 specifies that the nominal shear strength of a beam, V sub n, is equal to the contribution from the concrete alone, which is V sub c, and the component from the shear steel, V sub s. So V sub n, remember what I said before, anything followed by a little subscript n is the nominal strength. So we've been dealing with M sub n, that's the nominal flexural strength. V sub n is the nominal shear strength. And the ACI code basically codifies it so that there's a component VC that is from the concrete. And if you had a concrete beam with no shear steel in it whatsoever, then theoretically VC would be the strength of the beam. But if you do have steel stirrups in it, then you add VC to the VS for your total nominal strength V sub n. For the strength due to the concrete alone, VC, ACI 318 section 22.551 offers a simplified equation and a more detailed method based on table 22.551. The simplified equation can be quite conservative, but it's universal. It can always be used. And that equation is this. V sub c is equal to 2 lambda square root f prime c bw times d. That's equation 22551, where lightweight concrete shear factor lambda, if gamma is the design density of the concrete, then for all lightweight concrete with a gamma less than or equal to 110 pounds a cubic foot, then lambda is 0.75. Sand lightweight concrete, where gamma is between 115 to 125 pounds a cubic foot, lambda is 0.85. And for normal weight concrete, roughly 145 to 155 pounds a cubic foot, lambda is equal to 1.0. And the code does allow linear interpolation to be used between classes. Now, for the purposes of this class, I will tell you if we're talking about a lightweight or all lightweight or normal weight. I'll give you some indication if lambda is anything other than 1. Most of the time that we do these problems, lambda is equal to 1. Any questions on this? B sub W is the width of the beam or the web of an I-beam or T-beam. D is the same D that we've been using all along. It's the effective depth of the flexural reinforcement. Okay, so ACI 318, table 22551 offers more, there's a typo, offers a more detailed method for calculating B sub C. You can use the lesser of A, B, or C, where A is equal to 1.9 lambda square root f prime c plus 2500 rho w vu times d over mu times bwd, or 1.9 lambda square root f prime c plus 2500 rho w. This part drops out, and bwd, or 3.5 times lambda times square root f prime c bwd. Whichever of these three is the least is the one that you can use. And as you can see, you can really take advantage of this. 3.5 compared to 2 is quite a step up. 3.5 divided by 2 is 1 3/4 times more capacity just by doing a little bit more work. Okay, so the 2 square root f prime c works all the time, but sometimes one of these equations might get you a better answer. ACI section 2256 covers V sub C for pre-stressed members and members with axial compression, and section 2257 covers members with significant axial tension. For the scope of this class, we will only be using the simplified equation 22551, that's the 2 square root f prime c equation. But just so you're aware that these different conditions do exist. ACI section 9511 item B prescribes that Vn, it has to be greater than or equal to Vu. Okay, you're going to see this as a very common strategy of the code. It goes across all the boards. So what we've been doing again is the allowable moment capacity is Vmn. Now we're talking about the allowable shear capacity is Vn. And Vn must be greater than or equal to your factored shear load, Vu. And just a little bit of a tip off here, none of your homework or exam problems are complete until I see this comparison. That's the proof in the pudding that you know that you have the capacity that you need. ACI 318 section 21.2 and table 21.2.1 prescribe that phi is equal to 0.75 for shear. All right, so that's the capacity due to concrete alone. Now we can add to our capacity quite dramatically. A lot of times the steel is 5 or 6 times more capacity than the concrete alone. So this is a very significant part of your overall capacity comes from your shear steel. Shear steel comes in the form of shear ties. Okay, so here's a section of a beam, something that you're very used to looking at by now. These 8 circles down here represent your main flexural reinforcement, the reinforcement that you've been learning how to design and detail. But these hoops here that kind of go around the flexural steel, the vertical legs of these hoops are what's known as shear ties. So this hoop here is what provides the reinforcement for the shear. The circles down here are your reinforcement for flexure, and the vertical legs of this hoop is your reinforcement for shear. Shear can be in hoops, as shown here, or they can be in U-bars, as shown here. As long as the vertical leg is anchored with a hook or a horizontal leg of a shear tie, then this vertical leg can be used for shear reinforcement. You can't just terminate the bar at the top or bottom. There's no development, it would just pull out. But as long as it has a hook or a horizontal leg, then it's anchored and it provides shear reinforcement. The steel is oriented vertically and wraps around the flexural steel, as you can see here. Ties are typically number 3s, number 4s, or maybe number 5s, but they could be number 6s if you have some really big stuff. I mean, like Caltrans overpass girder type stuff, then maybe number 6s. Ties can also be formed by bending welded wire mesh into this sort of a shape or this sort of a shape. You can use mesh for your ties as well. Okay, so this is a side view of this. This is the end of the beam. This is where the reaction of the beam is. And this is just a cut point because the beam continues on to the right. You can see I have 2 rows of flexural steel, and there's my 2 rows of flexural steel running the length of the beam to resist flexure. Each one of these hoops or U-bars, if you look at it from the side, just looks like this, okay? If a beam is going to fail in shear, as I explained earlier, it creates a diagonal tension crack that looks like this. That crack goes all the way through the beam from one side to the other, and it starts at the bottom and makes its way to the top of the beam. If there is no shear steel, then once this thing cracks like this, it's pretty much done. It basically just collapses at this point of having this much crack. But with shear steel, all the shear ties that are crossing the crack plane are essentially stapling those 2 pieces together and allowing for a whole lot more load to be applied before the whole system fails. Okay, is everybody reading this? Is everybody understanding this is a section view and this is a side view of this situation? Okay, looking at the side view, we see that the struts provide a tension tie across the crack interface. Here, 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 and here. So if I designate that from the top of the beam to the center of my flexural reinforcement is little d, like it has been all this time, so this is what you've been doing, but I can also designate that the spacing of the ties is little s. Then we can say the strength contribution from the shear ties is equal to the strength of one tie, Okay, so one tie here has an effective area of AV. That's the cross-sectional area of the tie bar times the yielding strength of that tie bar. So every one of these hoops here gives you two legs of the size of that tie reinforcement times the yielding of that reinforcement. But you don't just get one tie helping you. You get 1, 2, 3, 4 ties in this case. So you have to multiply AVFYT times the number of ties crossing that crack, which is approximately N is the number of ties is equal to D, the effective depth, divided by S, the spacing of the ties. Now, why is a horizontal distance D designated as a vertical distance D? Well, because this D we know because we usually do our flexural design first, then we do our shear design second. So almost always D has already been figured out. We've already designed the beam and we know what D is. But D is a vertical distance, and the number of ties that are engaged is really based on a horizontal distance divided by the spacing between ties. But it still works because generally speaking, these ties are at a 45-degree angle. So at a 45-degree angle, the vertical distance is really the same thing as a horizontal distance. So therefore, the total strength due to steel ties is equal to, so Vs is the nominal strength of the shear ties, is equal to AV is the area of all the legs of the shear tie. FYT, little t stands for transverse steel. So this is the yielding stress of the shear ties times D divided by S. So this is our final equation for the strength due to shear steel. And this comes from ACI 318, section 22.5.10.5.3, equation 22.5.10.5.3. Where in this equation, A sub V is the total area of one shear tie. I say two legs in parentheses because the image shows you two legs, but you're not limited to, it could be one leg, it could be 6 legs. You're not limited to just 2 legs. It's just that most of the time they're detailed to look like this, and so most of the time it will be 2 legs. Fy sub t is the yield stress of the shear tie, which may or may not be different than the yield stress of your longitudinal steel. So that's why it's got the little sub t on it. D is the same D from the flexural analysis, top of the concrete to the centroid of the flexural steel. S is your spacing of shear ties. And ACI 318, section 22.5.1.1 specifies that V sub N was what's known as your nominal capacity is equal to V sub C plus V sub S. You just add them directly. ACI 318, section 9511, item B prescribes that, again, phi Vn must be greater than Vu. And so phi Vn then is equal to phi times Vc plus phi times Vs. Still must be greater than Vu. ACI 318, section 21.2 and table 21.2.1 prescribe that phi is equal to 0.75 for shear, as I mentioned a moment ago. But this 0.75 applies to VC and to VS. It might be tempting to use 0.75 for the concrete and 0.9 for the steel, but the code is clear. It's 0.75 for both components, VC and VS. Design load. Any questions so far? Okay, you know what I forgot to mention? I forgot to mention that unfortunately, lecture 7, this is lecture 8, lecture 7 unfortunately was lost in terms of the recording and the YouTube. Beyond my control, I apologize, but I walked out of here Thursday night and it was converting and downloading. And when I came back, the power had gone out and I had lost the computer, lost the recording, lost everything. So really the best I could do is go back a year last summer and I found the exact same lecture covering the same material and I re-uploaded that as lecture 7. So you might notice that I'm in a different setting and I'm wearing a different sweatshirt, but it's really pretty much the same thing. So forgot to mention that at the beginning of this. Hopefully that won't happen again, but can't control the power. Okay. For the design load, which is really V sub U is what we're talking about, is your design load. ACI 318 section 9432 prescribes that the maximum design shear VU can be taken as the factor of shear found at D from the face of support if all of the following are true. If your support reactions in the direction of applied shear introduces compression into the end region of the beam, now I'll explain that a little bit. If your loads are applied at or near the top surface of the beam, and no concentrated load occurs between the face of support and the critical section. If all three of these are true, then you can take VU to be the factored shear at a distance D from the face of support. Okay, so here's my design case. Reactions at the end, applied a factored linear load, W sub U. If I do my shear diagram, it looks like this due to a uniform load. And the highest point at the end here is my reaction, right? When you do your shear diagram, you find your reaction at A, reaction at B, you go up the reaction at A, down WU times L, up the reaction at B, gets you back to 0. So this is my factored reaction here. But I don't necessarily have to design for this magnitude of shear. I can design for something a little less. If my support reaction causes compression, which this does, my support reaction is pushing into the concrete, it's causing compression up into the concrete. So I pass A. If loads are applied at the top of the beam, which they are, so I pass B, and no concentrated loads between your reaction and your critical section, which I'll define in a second, which there are not. In this case, it's just a linear load. So I pass C. A, B, and C are all true in this case. So therefore, I don't need to design for RU, I design for VU. And then we take our shear diagram and we just truncate it at VU. So what's that distance? What's the distance here to here? Anybody still awake?
Not sure what that distance is.
Okay, well, that's an honest answer. At least you're awake. Anybody else awake?
Yeah.
All right, well, we're awake. Okay, the answer is right here. If D is the distance from the top of the beam to the centroid of my steel, that's D. then I can go from the end of the beam a distance d from the end of the beam. And where that intersects my shear diagram, that becomes my design VU. And my shear diagram becomes this shape. Again, I do not need to design for that RU, which is way down here. Okay, draw. If I continue this over, see how much bigger RU is than VU? The code's basically given us a little bit of a break. It says you only need to design for VU. And the reason why we're designing for VU at a distance D is remember that that crack has to come up at a 45 degree. So what we're really designing for is the average shear through the middle of that crack to the end of the beam. We're designing for that shear, not the shear at the end of the beam. Okay, so that's how it works. Okay, again, let me say it one other little visual here. This is RU that comes from my design, my shear diagram, right? This is the largest value on my shear diagram. I do not need to design for RU. I can design for VU. And that distance is little d. Okay, does that make sense?
Are we gonna be finding D, or is D will be given, or both?
D should be given because normally in a design process, you do the flexural design first. And when you do the flexural design, like you're doing right now for your homework number 3, you're determining what D is. So when you go to do your shear design, D has already been figured out. So generally speaking, I will tell you what D is, or the problem statement will tell you what D is.
Okay.
Okay, now the next thing we're going to talk about is when the shear gets to a certain value that is low enough, you do not need any ties at all. Or if you have a reinforced concrete beam that has just really low shear values on it, you may not need any ties at all. But you have to pass this criteria. So as you progress towards the center of the beam, the shear is decreasing, eventually hitting 0. There's your 0 shear here at some point, usually mid-span for uniformly loaded beams. ACI 318 section 9631 specifies that the minimum shear steel must be provided at all locations where VU is greater than this half times phi times V sub C. So if your VU is greater than that value, even if it's not very large at all, but it's greater than that value, you have to provide at least minimum shear steel. So in this diagram here, what I'm showing is from the end to this point, and from this end to this point, I have to have at least minimum steel. From this point to this point, I could, as a designer, say I'm not going to put any shear steel at all and just have plain concrete, and that is allowed. That's an engineering decision, but that is allowed by code. Okay, so let's talk about stirrup spacing limits and minimum shear steel. If VU is greater than 1/2 phi VC, then ACI 318 9633 and table 9633 require the greater of, and this is your minimum steel requirements. So AV minimum divided by S is equal to 0.75 square root F prime C BW over FYT, or AV minimum over S is equal to 50, the units of which are PSI, times BW divided by FYT. The greater of these two is the one that controls. If VU is greater than half VVC, then ACI 318 97622 and table 97622 prescribe the maximum spacing of transverse shear reinforcement as, okay, this is area of steel. This is maximum spacing. If VS is less than 4 square root F prime C BWD, then the maximum spacing S is the lesser of D over 2, or 24 inches. If VS is greater than 4 square root F prime C BWD, then the limits are D over 4, or 12 inches. So it's this whole tiered logic conditions. So you have to go in here. First of all, you have to calculate what your VS required is. And then is it more or is it less? Okay, if it's less, then it's the greater or the lesser of these two. And if it's more than this, then it's the lesser of these two. See, so you have to kind of like follow this logic train to figure out what the maximum spacings are. VS is required by design, not VU. Okay, so this is not your load. This is the VS as required by design. And also, this is not the VS as you're providing with steel. That's different. This is a VS as required by design. Okay, there is a third limit on spacing, S, that can be derived based on the required strength. So back to our basic proclamation that the phi VN is equal to phi VC plus phi VS has to be greater than or equal to VU. Well, then I can turn this around and I can say that phi VS has to be equal to VU minus phi VC. Then I can divide by phi and I can say that VS required is equal to VU minus phi VC divided by phi. That's how I get that VS to check the 4 square root criteria. Okay, and then VS is equal to AVFYT times D over S. I gave that to you a little while ago, is equal to VU minus VVC over phi. So therefore I can solve for my S required. And I just isolate S and divide it out by this. So S required is AVFYT D over VU minus VVC over phi. This here is a very, very handy equation to kind of skip through some of these steps and get your required shear demand. Depending on the magnitude of S, S is usually specified in half, 1, or 2-inch increments. Half-inch increments are usually used for spacings less than 4 inches, like 2.5, 3, 3.5. And 2 inches is usually for S greater than or equal to 12 inches roughly, 12, 14, 16, 18. So this kind of gives you just a rule of thumb as to how you pick a spacing. Tie spacing is usually tiered. So the smallest S occurs near the end regions with the highest shear, and then S may be increased for middle sections. 2 or 3 tiers at the most is optimal. Most of my designs are maybe 2 tiers, a heavy and then a light that carries you through the midspan. Lastly, ACI 318 section 22.512 limits the maximum allowable shear to VU must be less than phi times VC plus 8 square root F prime C BWD. So before I get to that one, what happens if VU is greater than this term? What do we do? Anybody? What do we do if we have a VU greater than phi times VC plus H square root F prime C BWD. What are the options? Anybody? We don't have any options? The point is, if you have a VU, a shear demand that is larger than this number, then you've overstressed the beam. No amount of steel is going to make that beam work. There is a limit where above that point, you can't get enough steel into that beam. The beam will just crush around the steel. So if you're at that point, all you can do is either figure out a way to reduce the load, reframe it, or look at it, or tell the architect, no, you can't have that 80-ton compressor up there, whatever. You either have to get the demand down, or you have to get this number up. How do I get this number up?
You increase the dimension.
Very good. You increase the dimensions of your beam. Absolutely. That's probably the most effective way to do it. So you can either increase the width or the depth or both. And when you increase the width and the depth, then VC over here, which is also a function of the width and the depth, goes up as well. So that's probably the most effective way to do it, is to increase the dimensions of the beam. A less effective way to do it is to increase the strength of the concrete. But I say less effective because the value for this number and VC itself is based on the square root of F prime C. So if I was looking at 4,000 PSI concrete, then the square root of 4,000 is 63. If I went to 8,000, if I doubled the strength of the concrete, then the square root of 8,000 is 89. So 89 over 63. So if I double the strength of concrete, then my allowable goes up 40%. See how that's not as direct. But if I doubled the depth of the beam, then I've doubled the strength of the beam. It's direct one-to-one. Okay, so this is a very, very important point that may be missed a lot of times, that folks think that no matter how big the load is, I can just keep putting in more steel until I get it to work. No, there is a cap, there's a limit. And above that, all you can do is increase the dimensions or increase the strength of the concrete or both, or figure out a way to get your demand to go down.
So Professor, if like there's a constraint for your dimension, you don't really have a choice but to change the concrete, right?
Or get the demand down in some way.
Oh, okay.
Yes, which, I mean, this is real world. I'm going through this right now. We're trying to increase the strength, but I can't increase the depth because of ceiling heights. So I'm looking at increasing the width, but not the depth, right? Because if I make it wider, it just takes up more room up inside the ceiling, and nobody knows that. Nobody cares. But at the same time, this is so big that we're basically just throwing our hands up at some point and say, you know what? And it literally is an 80,000 pound HVAC air conditioning unit. And we're saying, yeah, you got to spread that load out. You can't put it all on 2 beams. That's the problem. So we're taking both attacks to this. We're looking at making the beams wider. We're looking at using the finest pencil equation we can for VC to get the most value out of it. And we're going back to the architect and the mechanical guys and saying, it ain't working. You need to spread that load out or get the load down. So those are all viable ways to get this within compliance. And it's real world. It's stuff that we're dealing with just this week.
But in like economical side, like if you like make it like wider and taller, does that more expensive? And or if you change the type of cement that you're using?
That depends. That's a great question. And that really depends. If you're using normal grades of concrete, 4,000, 5,000, maybe 6,000, then that doesn't really change much. But if you were to try to go from 4,000 to 8 or 9,000, you could be doubling the cost of concrete. And that's huge. If you are adding 6 inches to the width and 4 inches to the depth, and it still fits within the architectural realm, then that's not adding a whole lot of cost. But if you're adding depth to the beam and there was no room for tolerance, so in order to add, say, 4 inches to the depth of the beam, then you got to make the building, every story has to be 4 inches taller. And if this is a 12-story building, then 4 times 12 inches is huge. And that ain't going to fly. See, so it depends on the situation.
Okay, makes sense.
Okay. ACI 318, table 20.2.2.4a limits the shear reinforcement usable yield for rebar to 60 KSI, even if the actual rebar grade is higher. Okay, so just in the last few years, 80 grade and even 100 grade rebar has come into a more common usage just in the last few years. We were aware of it maybe 5, 7 years ago, but it was exotic. It was like, ooh, that 100 grade stuff. Ooh, I'd like to see that someday. Well, it's a lot more common now. But even with the availability of, say, 80 grade rebar, you can spec it out and say, yeah, I want all the steel in my building to be 80 grade. Okay, no problem. But the code doesn't let you use 80 for shear design. So when you go to do this equation here, even if the rebar is grade 80, you still got to pop 60 into this FYT term. Okay. All right, so here's our procedure for shear design. This is what we do. We start by drawing a factored shear VU diagram. Then we calculate from that diagram what the VU value is at D from the face of support. That becomes our design value. Then we calculate our phi VC, and we use the equation phi 2 lambda square root F prime C BWD. We calculate this first because it usually is not a variable. We already know everything in it, so we can just go ahead and calculate it right from the get-go. If stirrups are required if you have VU, which you calculated here, greater than half phi VC, which you calculated here. Most of the time, stirrups will be required. Then you find your spacing by using S is equal to AV FYTD over VS, which is AV FYTD over VU minus phi VC over phi. Use this equation to determine your required spacing by demand. This one is by demand. Then we check our maximum spacing, This is by prescribed. So it's either S is equal to AV FYT over 0.75 square root of F prime C BW, or AV FYT over 50 BW, right? So whichever of these two is the least is your maximum spacing. And additionally, if VS required, which is calculated here, is less than or equal to 4 square root of F prime C BWD, then you use the least of D over 2 or 24 inches. If VS required, however, is greater than 4 square root F prime C BWD, then you use D over 4 less than or equal to 12 inches. And then you must confirm that VU is less than your maximum shear. Okay, so when we do homework problems, when we do exam problems, when we do problems, this is what we do. These are all the steps that we're looking for. Find your demand from the shear diagram, calculate phi VC, determine if shear stirrups are required, find your spacing by demand, find your spacing by maximum spacing, and find your prescribed maximum spacing. Confirm that your VU is less than the maximum. And I didn't put it in here, but most importantly, absolutely the most important step, confirm that phi VN is greater than VU. That is always your last step and the most important step. Okay, any questions on this?
You said confirm with BDU?
Let me write it out so that
Okay.
there's no confusion. Last step is you confirm that phi VN is greater than VU. Okay, it's the same with that we did for flexure. Confirm that your allowable strength is greater than your demand. Any other questions?
And then, Professor, for the maximum spacing, that S is the space between the two U bars, right?
That is the space between the U bars or hoops.
Yeah.
There's almost always more than two.
Okay.
Yeah, and I have an example. We'll do it after the break. I have an example that kind of hits home all these points.
Okay.
Okay, so why don't we reconvene? I don't know. Let's say 6:05 this time. I kind of cheated you last time. So let's say 6:05 and we will come back to do our example. right, is everybody back?
Yes.
Awesome. All right, let's walk through this example and see how this all comes together. Okay, so the example beam that we're looking at is going to be 14 inches wide, and D, as you know, top of concrete to the center of the steel, is 22 inches. Again, all of this would have been determined from the flexural analysis. The load that we have is 3 kips per lineal foot for dead load and 1.75 kips per lineal foot for live load. Concrete is 3,000 PSI. Our steel is assumed to be 60 KSI. And the concrete is normal weight, which is your code for lambda is equal to 1. As you can see from the illustration, we have 2 legs, and these are number 3 ties. Okay, so from that checklist, what's the first thing we do? We calculate our shear diagram. So the span is 20 feet, and we have to calculate what our factored linear load is. So we say W sub U, WD is dead, WL is live, WU is factored. So our factor load is 1.2 times 3 plus 1.6 times 1.75 gives us 6.4 kips per lineal foot. So my reaction is going to be the total divided by 2. So the total is 6.4 times 20 feet divided by 2. Each reaction factored is 64 kips. So that's the magnitude of this end, the magnitude of this end. Now, our VU is not at the end. Our VU is located at a distance D in from the end. So how do we do that? Well, we take our reaction minus our distributed load times a distance of D. So I take my 64 kips minus 6.4 is my linear load here times a distance of D. D is 22 inches, and I convert it to feet, and that gives me 52.3 kips. And this is my design shear at a distance D from the end of the beam. Okay, and this is how I've got it labeled. So at a distance, horizontal distance of D, this is RU at the end. This is my design VU at this point here. That's 52.3 kips. Any questions so far?
Yes, I have a question, Professor. Can you elaborate a little bit more why you multiply by their R sub U 6.4 times 20?
How I got to here?
Yeah, why'd you multiply by 20 feet?
Because that's the length of the whole beam.
So whenever, so you always multiply that by the length?
No, I kind of did a shortcut. Knowing that this is a simply supported, uniformly loaded beam, then I know that each reaction is the total load, which the total load is WU times the whole length divided by 2 because it's equally symmetrically loaded. But if you're not comfortable with this expression, you should always go back to statics and just sum your moments about a certain point and get your reactions by summing moments.
Okay, I just wanted to make sure about
Sure.
this.
Sure. Let me do this. Put it off to the side right there. If I sum about A, say the left-hand side is A, the right-hand side is B, right? Then this vector here is WU times L is the magnitude of the vector. And then the moment arm is half of L. So that's L over 2 minus my reaction at B times L equals 0, right? This is the more official way to do it. Why wasn't that? Get out of here. Get out of here. And now I can't change it. Love PowerPoint. Anyway, WU times L is the total load times L over 2. That's an L. So L over 2 is the moment arm minus R sub B times L equal to 0. And then if you solve for R sub B, then what you'll get is, see, R sub B goes on this side. So you have WL squared over 2 divided by L is WL over 2, which is what I have right here. So this was a shortcut of that. Did that help?
Yes.
Okay. All right. Next step. Find the capacity of the concrete alone, V sub C. So we're going to use our simple equation. V sub C is 2 lambda square root F prime C BWD. And this is why we do this first, because I know all the variables in this. I know that lambda is equal to 1 because the problem statement said normal weight. I know that the concrete is 3,000 because the problem statement said 3,000. I know the width is 14 from here. I know D is 22 from here. So there's nothing in this equation that I really need to solve for. I can just sum it up to 33.7 kips. So that part's done. Now, since VU is 52.3 kips, VU is most certainly greater than half of phi times VC, which would be 0.75 times this times a half, which is like 15 kips or something. So clearly VU is much larger than 1/2 phi VC. So therefore, I absolutely need shear ties. Okay, 12.6 kips. So this statement here says I have to have shear ties, right? So this is something that you'll do each time. You'll make this check and verify whether or not you have to have shear ties. Then we're gonna, now that we know we have to have shear ties, we can calculate what the spacing of those shear ties should be. So we're gonna use this expression. S required is AV FYD over VU minus VVC over phi. And again, plug and chug. I have 2 number 3s. The area of a number 3 is 0.11. Fy is 60, D is 22. My demand is 52.3. Phi VC is 0.75 times the 33.7 divided by 0.75. All of that is to say 8.06 inches. So I cannot put my ties any further apart than 8.06 inches, or I won't meet my strength requirement. Now we have our prescriptive requirements from the code, where S maximum is AVFYT over 0.75 F prime C BW. Again, I plug and chug my values. I get 22.95 inches. Or I check AVFYT over 50 BW. Same 2 times 0.11 times 60 KSI. Be careful of your units though. The 50 is in PSI. The yield is in KSI. So don't let that mess you up. And this comes out to be 18.86 inches. I also have my, the other 2 criteria that we have to look at, but in order to do so, I need to know what VS required is. VS required is VU minus VVC over phi. So I plug and I get 36 kips. Is 36 kips less than 4 square root F prime C BWD, which is 4 times 3,000 square root 14 times 22, which is 67.5 kips. So yes, VS required is less than 4 square root F prime C. So therefore, my spacing maximum is D over 2, which is 22 over 2 is 11, or 24 inches. Now I have all my requirements. I need to check requirement 1, 2, 3, 4, and 5. Which one of these 5 is the most restrictive? Which one of these is the least?
The 11.
As
8.
opposed to 8?
8.06.
8.06, yes. Okay, so you have to look at all 5. 2 and 3 are this maximum spacing thing. 4 and 5 are just prescriptive things, and 1 is based on the load. But of all 5, 8.06 is the least. So that becomes our maximum. Of the 5 requirements, 8.06 controls. Smallest spacing means the most steel per foot. So we're going to use S is equal to 8 inches for our end regions. You always round down, you cannot round up, right? So if this number had been 7.8, you can't go to 8 inches. If it was 7.8, you have to round down to say 7 inches. Everybody okay so far?
Is that because you kind of want to add more the U bars so it has more shear strength?
Yes. Yes. You can always add a little more steel, but you can't have less steel than what's required to carry the load.
Okay.
But you can't space them out more than 8.06, right?
Right. Yep, that's right. You can't space them. You can always space them less than whatever the requirement is. You can put them, I could put them at 6 inches if I want. I'm just spending somebody's money, but I cannot put them at more than 8.06. And so then it won't meet the final strength requirement won't be met. Okay, so per above, the maximum spacing anywhere on the span is 11 inches. Okay, so this was based on the shear demand. These are prescriptive. So this one changes as you go down the span because this number right here, VU, gets smaller and smaller as you get towards the midspan. So this one varies, but these don't. All 4 of these are not based on the load. They're based on these prescriptive requirements. And the one exception is you may, if you were VS required, kicked you above 4 square root F prime C, then you may get to a point on the span where you're below 4 square root F prime C, and these last 2 might change. Disclaimer. But in this case, we're already below 4 square root F prime C, so these will not change. So of these prescriptive 4, the 11 is the one that controls. So nowhere on my span can I use more than 11 inches because of these prescriptive requirements. Even if the load goes to 20 inches, I still can't put them more than 11 inches apart. So what I'm going to do is I'm going to figure out, since I cannot put my ties at more than 11 inches anywhere on the span, let's figure out where I can put them at 11 inches by design so that I know where I can create that tier. So for S equal to 11 inches, what is my capacity, phi Vn? Okay, so phi Vn is equal to phi Vc plus phi Vs. Phi Vc is still the 0.75 times 33.7. But the phi Vs I can calculate as phi times the area of steel times the yield times D divided by my desired spacing of 11 inches. And this gets me 51.7 kips. So you can see when my shear demand was 52.3 kips, 11 inches doesn't cut it. I don't have enough strength. But if the shear demand is at or below 51.7 kips, then I do have enough shear capacity at 11 inches as opposed to 8 inches. So from similar triangles, If my reaction at the end is 64 kips, and that's at a distance from the center of 20/2, then I can solve for x from the center to find out when does the shear go at 51.7. And that answer is 8.08 feet from the center of the beam. So put it graphically, the reaction at the end is 64 kips. My design shear is 52.3 kips, but at a distance of 8.08 feet from the center is when the shear demand drops to 51.7 kips. So what that means is I have to cover, let me try to draw this in here. Do I have a paintbrush? I have a stamp. I don't think I have a, oh, no, that's a circle. Oh, whatever, I'll squiggle. From here to here, I have to put my number threes at 8 inches on center. But from here all the way to the symmetric side on the other side is where I can put number threes at 11 inches on center. So I have two tiers. I have a closer spacing at the end, and I have a slightly wider spacing through the middle. And to figure out where I can put that break between the closer spacing of 8 inches and the wider spacing of 11 inches, I figured out the capacity of my system with number threes at 11 inches and figured out where that spot was. And that told me where I can make that break. Okay, any questions on that?
I have a question, Professor.
Sure.
So first you chose the 8 inches, and why, like, after that you chose the lowest one again? How did it go? Like, how did you choose 11?
Because of the 4 prescriptive requirements, 11 was the lowest number.
Mm.
So I cannot exceed any of those 4. All 4 of them I cannot exceed, but the lowest number is the one that's going to control, and the lowest number was 11 inches.
Yeah, so first you picked the lowest, for you chose 8, and then you picked the second lowest?
I picked the second lowest because it's prescriptive. Nowhere on this span can I have number 3 spaced further than 11 inches. So because I know that I can't go any further than 11 inches anywhere on the span, I figured out where on the span does 11 inches work by design. And that's this magic point right there at 51.7. When the shear, my design shear was 52.3, I needed them at 8 inches. But when the shear drops to 51.7, now it works at 11 inches.
Yeah.
But how do you know, like, how are you gonna know if you can use the bars, like the number 3 bars all the way or not?
Well, there is a section here in the middle. Let me wipe all that out. There is a section somewhere in this middle region, right in here to here, where the shear demand is so low that I might be able to not use any ties at all. But you have to calculate, where does VU be less than 1/2 VC? And wherever that number is, from that point to the center, you may put no ties at all. And that's the only exception to this 11-inch rule. But most designers that I know, don't do that. You can by code, but most designers do not do that. And the main reason why they don't do that is because this assumption of a linear load may not be good. You may get some skip loading in here, like I explained about live load. So you make it that with a skip loading, that you make it a shear diagram that looks like this. And so where this low center point shifts off to the side, and you may miss that, or you may get a shear diagram that looks like this, and where this low point is shifted off to the right. It gets complicated, and a lot of designers don't see any benefit of trying to just eliminate a couple of ties in the middle. So most of us will figure out what we need at the end based on our load demand of 52.3. And then we'll figure out what can I run for the rest of the beam based on prescriptive requirements. And then we figure out at what load can we transition from the higher steel to the lower steel. Any other questions on shear?
I have a question, Professor. So, in real life designing, do is it always like there's two spacing or something? Is it
Tiers.
like
Tiers. Usually it's 2. Many cases I'll do 3 if they're longer spans. If it's like a, I don't know, 20 to 30 foot long beam, generally it'd be like 2 tiers. But if we're talking like a 45 to 60 foot long beam or a double T or something like that, I probably would go to 3 layers, 3 tiers. But in this case here, it doesn't make any sense at all to go to 3 tiers because you have such a little difference between your heavy and the light. I mean, what would your middle tier be? Number 3 is at 9 inches? That doesn't make any sense. So this case, 2 tiers. And in fact, if I was designing this beam in real life, I would have just went number 3 is at 8 inches, the whole length of it.
yeah,
'Cause
I
it's
was gonna say that one.
Yeah,
Like,
because it's very little difference. But back to real life, the real life difference is much more profound. A very common beam reinforcing schedule that I will use is number 4s at 4 inches for 5 feet, then number 4s at 6 inches for 10 feet, and then maybe number 3s at 12 inches for the middle region. And that's something I would use in the real world fairly commonly.
at any like given load.
Well, no, that's not with any given load. That's with loads that we deal with fairly
Okay.
commonly. We do a lot of parking garages, so the loads are pretty the same over and over.
Okay.
Yeah, but we do some interesting things. We do some unique things, and I've got some beams out there in the real world out there somewhere that are. I got some monsters out there. I got some beams that are like 45 feet long. They're 5 feet deep. They're taking nearly 1,000,000 pounds at each end for a reaction. And I've got number 5 quadruple legs. So 4 legs of a number 5 at 3 inches on center for a beam that's 5 feet deep. So there's some big stuff out there. But that's nobody's dream of common. Those are very unique.
So like in your homework, do you tell us like if we're gonna have 2 tiers for the design, or do we need to like
I
know
don't
that
rem
one?
I don't remember. I gave you enough information, but I don't remember specifically.
Okay. Thank you.
Sure.
Yeah.
Alejandro?
Yeah, I think just the confusing part for me is when to transition from a number 3 bar to a number 11. Because you're saying the number 11 bars are,
Wait. Back up.
sorry, the
Get-
number.
Make sure you have your terminology right.
It's the same bar, it's just
yeah.
different spacing.
Right.
Yeah, yeah.
And I'm not picking on you by any means, but I'm just saying for everybody, please make sure you get that terminology. The bar size is a number 3 throughout the whole beam. The
Just-
spacing is what transitions from 8 inches to 11 inches. The OC is not for Orange County. The OC is on center. So that is your spacing. And again, not picking on you. I just want to make sure everybody is super clear that the bar size of those stirrups remains constant. The only thing that changes is the spacing.
Yeah, because we look at the smallest one, which was 8, and then that's what you use for the V. Let me see.
For the VU.
That's what you use for the VU.
Yes.
But
Now,
then after that, you looked at the second lowest, which was 11.
yes.
That's just the part that's a bit confusing for me right now.
Okay. Understand. So I think, yeah, that's the end of the presentation. What I would do is go back and review this part.
Okay.
This part right here. This is where it's all at. You have 5 requirements.
Okay.
One of the 5 is based on the load. There's the load right there.
Okay.
The other 4, like I said, with the caveat that you're in this tier, but the other 4, there's no load in these equations. They're prescriptive. So these 4 do not change as you go down the beam. So if it's 11 inches controls, it's 11 inches for the whole length of the beam.
Okay.
But for this equation, this one changes
Because-
every foot of the beam because the shear changes every foot of the beam.
Got it.
Okay. Okay. Anybody else? Any other questions?
Yeah, Professor, the last 2 equations can be changed, right? If it's bigger than, yeah, these 2. If it's
Yes.
bigger,
Yes.
but the process is the same, right?
The process is the same. Yes, if the shear demand here had been much larger, see this 67.5, if the shear demand had been, say, 80 kips, actually, no, it would have been much like 100 kips. If the shear demand had been 100 kips, then you would have been greater than 4 square root F prime C. And your maximum spacing would have been D over 4, which is 5.5 inches, or 12 inches. And then as you go from the end towards the middle of the beam, at some point, you would go from above 4 square root to below 4 square root, and these 2 would change back to 11 and 24. So that's the only caveat. These are not based on the load, but the tier that you're in is based on this load. So this could change. If you're in the higher tier, at some point it'll go to a lower tier. But apart from that, the point is these 4 are not based on load, they're based on prescription. Only number 1 is based on the load.
Okay.
Okay, so take a stab at this. This is one of these things that you kind of have to soak in and study a bit and try the homework problem. And then by all means, come back with your questions and I can answer those then. But I think it takes a little soaking to kind of know what to ask. So as an update, we are now in chapter 8. We hopscotched over chapter 6 and 7. We're going to hit those next, but we're through chapters 1, 2, 3, and all of 4 and all of 5. Now we're in chapter 8. And then next lecture on Thursday, we're going to go back to chapter 6 and start talking about deflections and cracking. Not sure yet what we're going to talk about on the 6th of July. What kind of, if we have to catch up, we'll do it then, or we could get a jump start on column design. I'm not sure where we're going to be just yet at July 6th. But for everybody, please make a mental note that July 8th is our midterm. Yeah, we can do a little review. on July 6th. We can kind of review it a little bit. But what I can tell you at this point, a week and a half away from the midterm, what I can tell you is you should start studying for that midterm. Don't wait till the last minute. And the scope of the midterm is going to be chapter 1. I believe it's, shoot, now I have to go back and it's definitely lecture 1 through analysis of T-beams. What I don't remember is if doubly reinforced beams is on the first midterm. But I will check on that. I'll have an answer for you on Thursday, whether or not doubly reinforced beams is on the midterm, but definitely everything up to that, including T-beams, will be on the midterm. Shear and deflections most definitely will not be on the midterm. I'm going to save those goodies for the final. Okay, I had a question about zooming. And the answer is yes. What we're going to do is we're going to use Zoom on the night of the midterm. The midterm is going to be our normal, regular scheduled class time, 5 o'clock to 7:05, I believe. And we're going to use our regular class time. You connect to Zoom just like you always do for the lecture. And when you connect to Zoom at 5 o'clock, what you're going to find is I'm going to have a list for you by name, and it's going to have a number of which exam for you to take. And then you're going to go on Blackboard and you're going to log into your exam and you're going to take that exam on Blackboard. When you're done taking the exam on Blackboard, you are going to scan and PDF all your handwork, and you're going to upload it to a assignment called midterm. So there's going to be an assessment or a test called midterm, and you pick the number assigned to you. And then there's going to be like a homework assignment called midterm, and that's where you upload the PDF of all your handwork. So that's how that works. And the test will be timed. It will start when you start, it will finish when you run out of time. And then it will automatically shut down and submit your results. So that's how the midterm is going to work.
How many questions?
3 usually. 3 usually. Each one of them has 3 or 4 parts, and they're all going to be calculation essay type questions where I actually ask you to calculate all or part of whatever the question is asking. It will be like the homework, yes, but a little more defined. Not as open-ended design questions like the homework, because I have to design it in such a way that everybody comes to the same answer.
Quick question, Professor.
Yeah.
How much time do you give us on the final?
The allotted class time.
Okay. Perfect. All right, thank you.
Sure.
So, Professor, we will submit the solution as a PDF, or we submit it on Blackboard like an online exam?
That's a great question. It's actually both. So what you're going to find is that the online Blackboard version of it is a essay question where you actually open up a PDF that shows you what the question is, and then you fill in the text box online with your answer. But then after you've submitted your test with just a quick little part A, 260 kips, part B, 3 inches, whatever those answers are, and then you submit your midterm, then what you do is you scan to PDF all the handwork that you just did to get to those answers, and you submit those to the assignment called midterm. And the reason that we do this is the midterm is worth 50 points. So each question is worth 15 to 20 points per question. And if you got the wrong answer, there's no way to pass the class if you got a wrong answer, and I can't give you any partial credit because I can't see your work. So the way that we do this is you put in your answers, but then you scan your handwork so that I can scan your handwork and look for partial credit.
I see. Okay. So you will be asking like specific question, not similar to in the homework that we have like more elaborating questions. Right.
No, it's going to be a lot like the homework, but what I'm asking for will be a bit more specific.
Yeah. Okay.
Okay.
Quick question, Professor. Like for the Blackboard questions, is it gonna show us all of the questions, or do we have to answer one question to move on to the next one?
My understanding and way I set them up is that you do not need to go from 1 to 3 in any particular order. You can open them all up. You can do whichever one you feel most comfortable to do first. The order of how you do your work is not important to me. It's just that you finish.
Okay, because I like sometimes I go back to different problems sometimes.
Right. Yep, no problem. I had a private question that said, do you post the solutions to the homeworks? You should see those. I have posted the solutions to homework 1 and 2 so far, and hopefully tomorrow morning I will post the solution to homework 3. Okay, so we'll talk a little bit more. Like I said, we got this whole July 6th thing to really kind of hone in on all the details of this, but I know you need to start studying earlier, so I wanted to give you the scope. The scope will most definitely be everything up till the 22nd, including T-beams. I just need to check my notes and see if doubly reinforced beams is on this test, or am I saving that for the final? And I'll get back to you on Thursday with that. Any other questions anybody like to ask of me tonight? I guess one final thing to make sure everybody understands. I really cannot allow makeup exams. So the midterm has to be taken at the time that we all do it together. You do not need to be on Zoom the whole time. You do not need to show your face. You don't even need to unmute. If you want to be on Zoom, it is to your advantage because you can ask me questions anytime during the exam. You can ask me a question, a clarifying question, and I'll be right there. But if you choose to not stay on Zoom and to do the exam in your own leisure, in your own private, that's fine, but it's still due at the same time as everybody else. So please make sure you understand no makeup exams will be allowed. Do not get sick. Do not get the measles. Do not break your leg. Be there. And other than that, compromise tests will not be credited. So this is really kind of the last time I think we're going to be doing this whole COVID thing. And let me outline for you, just take a minute here. The expectation is that you're taking this test under the same conditions as you would be taking this test if we were doing it back in the classroom, like we will be starting in the fall. So the expectation is that what is in front of you to take this exam is your calculator, your textbook, and your single page 8.5 by 11 of notes is what's allowed. The notes must be handwritten. They cannot have any pictures, any printed material, nor any examples that you may have gotten from anywhere are not allowed. All you can have on your single page in notes is just your notes of what's been presented in the lectures and the textbook. That's what is expected. Your textbook, your 1 page in notes, your pencil, and your calculator, and nothing else. Not your cell phone, not your laptop, except for you need the computer to see the test. Other than that, duh. But besides that, there should be a bare, empty desk. That is the expectation. Now, I understand that I am not going to be sitting next to you while you take this test. So I can't visually verify that is exactly how you're taking the test. But I wanted to make it clear that is my expectation. This is going to be on the honor system, at least for 1 more semester. This is going to be on the honor system. But if I do find evidence of any kind of cheating, let's be clear, that test will be scored with a 0. You will get 0 for that test. And the midterm's worth 40%. So a 0 on 40% pretty much dooms you that there's no chance you can pass this class. So don't cheat. And again, that's my expectation. So not to be what are the doom and gloom, not to be a downer, but I want to make sure we all have the same expectations going into this test. Any last questions for me?
Yes, Professor. There was a question in the chat, and I had the same one. Do we have to submit our notes?
Yes. Yes. Oh, I'm sorry. Yes, your note. I'm sorry, I didn't say that. Yes, please. When you scan and submit up your handwork, please submit that 1 page in notes along with it. And thank you for asking. I forgot to mention that.
Thank you.
Anybody else? Simon, I think you had the same question.
Yeah, I have a question, Professor.
Sure.
I know we went over T-beams, but we didn't do any in the homework examples. Would that be we tested on T-beams?
Yes, the T-beams are included in this. Trying to remember where we did it. I think we possibly did them on homework 4.
Yeah, we're on homework 3 right now.
Right. But I assigned, I think I put up homework 4 today. Let me take a look. Bear with me a second. Yep, there's homework 4. So there's your T-beam.
Got it.
And this is a T-beam as well. So yeah, homework 4 has the T-beams. I do acknowledge that you're not going to get a lot of feedback on them because you're going to be turning them in on the 6th and the midterm is on the 8th. So no, I'm not going to have a chance to grade them, but you will have a chance of going through them and practicing that design. So that is why T-beams is on the exam, and I'm pretty sure, I guess I'll double check, but I'm pretty sure that doubly reinforced beams are not on this exam because I think those are homework 5.
So we will be able to look at the solutions before the exam for T-beams.
Yeah, you will. I'll post those solutions Wednesday morning.
Got it.
Good questions. Thank you. Anybody else? All right. We'll, like I said, we'll talk about it a little bit more before the exam, but I wanted to give you an early warning of what's expected and what to anticipate. So with that, I will close this out and we will see you on Thursday.
Thank you, Professor.
Thank you, Professor.
Hey, thank you, everybody. Good night.